Hello to everybody. Thank you very much for joining us at West Midlands Cibse's latest CPD offering. I have great pleasure in introducing Will Pitt. Will, I met a few years ago at BESA and at their technical committees, and he talked passionately about the subject we're going to talk about today, about fixings and supports and what have you. And I'm pleased to say he went on to develop a technical standard that is a very, very good read if you get a chance, but I'm sure Will's going to give us all the information and what have you that we need on that subject now. If you could please save your questions to the end of the presentation and then add them into the chat, and we'll take it from there. Thank you very much. I'm going to hand you over to Will. Thank you.
Thank you very much indeed, Martin. I'm just going to put my slideshow on now. Okay, and Martin, can you confirm that you can see my screen in presenter mode? Can you see that okay?
Yes, that's fine.
Excellent. Okay, let's go. Right. First of all, welcome to you all. Thank you very much indeed for joining us today. Good afternoon. Just to introduce myself, so my name is Will Pitt. I'm chair of the BESA Technical Committee. I'm also technical leader at Lang O'Rourke. Now, this guidance has been produced collaboratively by members of the BESA Technical Committee, and that comprises technical representatives from the MEP contracting sector and also the main contracting sector. Now, the group felt this was an area of work where technical guidance was very much lacking in the industry. So supports and fixings are a crucially important but often overlooked element of building services engineering design and installation. They're often considered as commodity items where procurement decisions are often made solely on price, or worse still, changed on site without the knowledge or the implications of what that might mean. The reality is that getting supports and fixings right and being able to demonstrate that requires a much more rigorous approach from everybody in the supply chain, including the designers. So I thought it'd be useful just to kind of kick off with how the industry has historically operated in the area of supports and fixings and how they've approached supports and fixings. So we use channel, we use threaded rod. Do we understand what we're selecting and whether it's fit for purpose? We traditionally fix to steelwork and we fix to purlins in roofs. Again, are we understanding the implications of doing that and the loads and so on? We often mix and match products without understanding whether they're tested together and what the performance of that is as a system. But crucially, site teams are often left to come up with solutions themselves without having the information or the knowledge or the skills potentially to be able to make that decision. So what does that all mean? Well, it means that we don't know what the applied load is. We don't fully understand the application. We rarely seek approval from the structural engineer, and therefore we can't prove that selected supports and fixings, all the systems are fit for purpose. But you might be asking yourself, what does that matter and why is any of that a problem? So let's have a look at the reasons or the need for change. Firstly is clearly safety. Getting supports and fixings wrong can be catastrophic. You may have seen this image before, but this happened back in 2009. 12 school children were injured when a ventilation duct collapsed in a school hall during an exam. The failure was later found to be as a result of inadequate supports and fixings generally. Likewise, you may have seen this image. This was floating about on social media about 12 months ago. The entire installation of a large diameter pipework system failed, and as you can see, it's caused significant damage. Now, it was understood from the subsequent investigations that they'd found that the fixings had been incorrectly selected, incorrectly installed, and that the selection was changed on site. But why else do we need to look at change? Well, the second reason, in my view, is around the subject of cost and reputation. Clearly, if that had happened to your company or a project that you've been working on, There's going to be significant cost associated with that, but I think more importantly, the reputational damage that it would create to everybody involved in that is substantial. The third reason, I'd like to introduce you to a British standard, which is BS 8539. Now, this particular code of practice has been around for a number of years, in fact, nearly 10 years, but it addresses what's actually called a code of practice for the selection and installation of post-installed anchors into concrete and masonry. So it's not the most exciting of subjects, but essentially what this standard does is it sets out a framework for everybody involved in any fixing into concrete. So it's not just the construction industry, it applies to all sorts of sectors, but it sets out a framework for design, selection, installation and testing to ensure that there's a full audit trail throughout that entire process. And that's something that is very much coming to the fore in the construction industry. And lastly, for me, is around due diligence. If you were a client on a project, for example, a data center or a manufacturing facility, you would be within your rights to ask the contractors and the design team involved in that project to prove that the supports and fixings that might be supporting, I don't know, heavy pipe work above a data hall or whatever it is that you put, can you prove that that entire system has been correctly designed and that you can evidence that and that the whole thing's been installed correctly? And I think in my view, the industry historically hasn't been very good at that, and normally people would struggle to be able to do that. Just some examples on the screen of some common issues that typically can occur in construction projects. The first image on the left is a roof purlin. Now, this roof purlin has been overloaded because the supports or the services have been suspended off of that, and the consideration wasn't put into place as to whether that roof system could actually support the load. The second image on the left here is showing electrical services that are supported from a trapeze and drop rods, which is bracketed to a steel column. And if I just bring my mouse over to here, you can see that you've got what is happening here is you've got a cantilever. So most of the load is applied onto this side, and the support back to the steelwork will almost certainly be overloaded. So it's really not fit for purpose, that system. And then the final image over here is a really good example of what we call a complex load path. So if you look down at the bottom, we've got what appears to be a sprinkler pipe work, which I think has probably been added on later on as a parasitic load. Now, the problem here is it's very difficult to trace back where that is going back to the main structure. And as a result, it's probably wasn't taken into account when that bracket was designed in the first place. So other common issues that we experience across the industry include mixing and matching of products, the base substrate not being suitable for the fixing, which we'll talk about in a bit, insufficient secondary steelwork, and roof plant not being structurally assessed for wind and snow loadings. So how can we do things differently? Well, BESA TR50, the Guide to Good Practice, sets out a best practice approach starting at design. Now, supports and fixings may not be uppermost in the mind of construction professionals during the initial design stages. However, it's important that certain aspects are addressed by the designer at this stage in the process. It's the responsibility of the mechanical designer to calculate the weight of building services systems in order to obtain approval from the structural engineer that the building structure can support the weight of the MEP services design. Now, specifically, there are two areas of this. I think, first of all, there's suspended services. So structural slabs are usually designed with allowances for suspended services. However, there have been examples, particularly in heavily serviced buildings, where this hasn't been the case and they've actually been overloaded. Other examples are where you've got a heavily serviced building that might be in a lightweight steel frame structure. A data center or perhaps a manufacturing facility being good examples. And the other area of design is particularly around roof plant. So for roof mounted plant and equipment, designers should be obtaining confirmation from the structural engineer that the roof structure has been designed to accommodate the weight of heavy items of mechanical plant, including where applicable, any requirements for plinths or upstand details. It may also be necessary to restrain roof mounted plant and equipment depending on the calculated wind and snow loadings. Now, there have been examples in the past that I've been aware of, particularly in design and build contracts, where MEP contractors have ended up taking responsibility and the structural design hadn't made sufficient allowance for roof mounted plant. And there are other examples where they've been left footing the bill for significant amounts of secondary steelwork. So this evaluation should take place at REBA stage 2. My printer's going mad, sorry about that, and no later than REBA stage 3. Okay, moving on now to specification, and particularly the importance of the correct specification. So supports and fixings, products and systems should be specified in collaboration with structural engineers and the fixings manufacturers. To enable them to be correctly selected and specified, the following factors need to be considered. Now, firstly, loading. As we've just talked about on the previous slides, the loading, it's really important that that's calculated accurately by the designer. And that should include things like if it's pipe work, the weight of the water in the pipe work, the insulation, and ideally the self-weight of the bracket. And I know that through the increasing use of Revit software that there are capabilities to be able to do that within that. But it's something that I think is really important, that even in a design and build project, the designer should be advising on the weight of the services. The next issue is the base material suitability. Now, BESA TR50 provides guidance on this, and it includes areas such as a definition cracked and uncracked concrete, what that is, fixings to purlins, and also fixings to composite metal deck floors. Environment, another thing that needs to be taken into account. So certain environments, good examples being swimming pools, external plant areas, any building near the sea, or perhaps in a tunnel, you're going to have enhanced corrosion requirements, and that needs to be taken into account when you're specifying the support and fixing system. Now, the next thing in terms of specification is the subject of fire rating. Now, for specific applications, it may be a requirement to ensure that supports and fixings are specified to be able to withstand a prescribed fire exposure or period or rating. Now, this is touched on in the guide, and it's very much an evolving subject in the industry at the moment. There isn't a single specific UK test standard that covers fire ratings of supports and fixings as a single entity. There is guidance that talks about the fixings or the anchors into the concrete. There's guidance in relation to the drop rods, but there's nothing that talks about it as an entire system. And that's something that I think is desperately needed, and certainly at BESA we will be looking at that over the next year or so. In TR50, it does give some best practice examples of where fire rated supports and fixings will be required, and provide some considerations and watch points. So these include, firstly, supports for power supplies to life safety, firefighting and other critical applications. You may be familiar with BS 8519, but that has a requirement that the supports for life safety power supply should have a survival time that is equal to that of the cables that it supports for the same defined fire conditions. Now, there are two options for approaching this, really. You can either split out the life safety supplies into a separate containment system, as shown here, or if it's a single module, which is commonly used in DFMA processes these days, you would need to look at providing a fire rated support and fixing for the entire system. Second area is supports either side of penetration seals. So fire stopping and service penetrations either side of compartment walls, that should always be part of a manufacturer tested and approved fire stopping solution. And that will have a requirement that the support either side of that which will be typically no more than 500 millimeters, they should be fire rated as well. And the third area of fire rated supports and fixings is designated fire escape routes. So for example, if you've got a fire escape corridor that has a 60-minute or a 90-minute fire rating. Now, this is very much a contentious area because there is a school of thought that says if you've got a designated escape route and you've got services in the corridor above that, then by definition, there will be no fire load in that escape corridor. Therefore, why are we looking at fire rating the supports and fixings? And I think the key message here is it needs to be looked at on a project by project basis, and it may well be that you could come up with an engineered approach. Excuse me. Okay, so moving on to support spacing. Particularly for pipe work and ductwork services, they should be provided in, the spacing should be provided in line with manufacturers' recommended support distances. So in the absence of any specific information, vertical and horizontal supports for copper and steel pipework can be based on BESA guidance in TR50, and ductwork would be DW144. So where you've got a multi-service bracket, the support spacing should be based on the service with the most onerous requirement, which typically might be a copper pipe. Thermal expansion. Now, in addition to static loads, pipe movement as a result of thermal expansion and contraction may also impose additional active loads onto supports. And that is really very much dependent on the pipework expansion design strategy, but it's something that needs to be thought of, or may need to be thought about when you're looking at the support and fixing system. And finally, in terms of specification, is the subject of approvals. Now, BESA 8539, the concrete specification we talked about earlier, that has a requirement that wherever possible, ETA rated anchors should be used for any fixings into concrete. Now, ETA stands for European Technical Assessment, and essentially this is a harmonised standard which is used by all reputable fixings manufacturers. And as part of that testing process, they've tested their fixings and anchors into various substrates, and they're therefore able to publish the performance data for those particular anchors, and that should be used as part of the selection process. Moving on to installation. Now, this may not be something that as mechanical designers you necessarily get involved in, but I think it's important to have an awareness of this subject. So it is essential that installers undergo manufacturer-specific training before work commences. This may take the form of a toolbox talk on site, although some fixings manufacturers have developed very good online training videos. Now, for fixings into concrete specifically, again, referring back to BESA 8539, it's a requirement that all anchors are installed by trained individuals working under competent supervision. Now, in order for somebody to be deemed competent, according to the 8539, they should have undergone and completed a competent supervisor training course, such as that delivered by the Constructions Fixings Association, as you can see on the screen. Okay. Now, sticking with installation, I wanted to talk about torque settings now. Many of the support and fixing systems used in building services actually have specific torque settings that will be specified by the manufacturer. Now, this isn't, in my view, something that the industry has done at all well. If you think of the automotive industry, or even if you look at if you're a cyclist, you'll know about that road bikes, and there'll be specific torque settings for different components. And essentially, why should our industry be any different? So examples of products that have specific torque settings include beam clamps, channel nuts that are used on framing systems and trapeze rods, fixings to purlins, beams and metal decks, and torque controlled fixings into concrete. And it's important that when these are installed, that it is evidenced that these have been torqued to the correct setting. Okay, now we've selected the fixings properly based on the loads that have been calculated. They've been selected based on ETAs. They've been installed by trained operatives working under supervision. Now we come to the testing. Now, the key point here is that there are only two types of fixing test, and that is one, a proof test, and two, a preliminary test. You may have heard people in the industry talk about a pull-out test being used, and the advice is that that shouldn't be used because it's generally misunderstood and too vague. So proof test and preliminary test are the two terms that should be used. So what are they? Excuse me. A proof test essentially is only there to validate the quality of the installation. So as I mentioned already, if you've gone through that process of being able to demonstrate that it's an ETA approved anchor that has been selected based on a calculated load, it's been installed by competent individuals working under supervision, if you've got that audit trail, there is no need to even carry out a proof test. However, if one is required on site, a proof test is only there to validate the quality of the workmanship. A preliminary test, on the other hand, is something that is carried out on site to determine the allowable resistance, otherwise known as the maximum working load. And that would be used in a case where there isn't any characteristic resistance or recommended resistance available. So a really good example of where you would carry out a preliminary test would be in a refurbishment project where the concrete performance isn't known. So you would test that fixing to destruction to determine the allowable load. Proof test, preliminary test, two terms, two forms that should be used. Just to finish off then, really, I've got a couple of examples of good and bad practice that are in more detail in the guide. The first example here is fixings to purlins. Now, purlin clips should be avoided unless permission to fix them has been obtained from A, the purlin manufacturer, and also the project structural engineer. Now, subject to that approval from the structural engineer, the preferred fixing mechanism is actually to drill through the purlin itself. Hanging anything off the purlin lip should be avoided because what you'll find is that the loads will be minimal and anything other than a light fitting just won't be taken. Window brackets, another good example. We see this a lot in particularly in large steel frame buildings. You often see a single window bracket used, and that is unacceptable. Wherever that is the case, there should always be one either side of the I-beam. And finally, overloading of fixings. So when you're designing brackets, services should be evenly distributed as possible through all supports and fixings. And also services hung on the bottom of other services, that parasitic load should be avoided because it can create cantilevers and multiple forces acting on that bracket and lead to potential to failure. So it's all about sort of being able to demonstrate that what is installed is based on a designed process, and you can demonstrate that as well. So just to summarise, gone through quite a lot in a short period of time. We should be establishing the weight of suspended services and roof mounted MEP plant, and that should be something that should be carried out by the designers. We should be collaborating with the structural engineers and the builder to obtain the approvals that what we're doing is acceptable. Products should be selected based on that weight, based on the application, and also based on the environment that we talked about earlier on. Now, this is a really key point. Details should be provided on installation drawings on the bracket design. This is a kind of a bugbear of mine because in general this isn't done, but we need to get back to a point where this is done. For those of you that were in the industry sort of pre-design and build era 25 plus years ago, a consultant design would typically show bracket details. Now, I'm not saying we're going to get back to that, but as an industry, we've got to get to a point where more detail is shown on drawings to enable those on site to install as per the drawing. Operatives should be trained based on best practice installation techniques. We should only be installing using the correct tools, following manufacturer's instructions, including torque settings. We should be testing the fixings based on 8539, so a proof test or a preliminary test, depending on the type of application. Is it a new build or a refurbishment? Excuse me, it's my phone ringing. And finally, just to conclude, so supports and fixings are not commodity items. They need to be designed and engineered from the outset and not left to those carrying out the installation to come up with solutions. More information on this whole subject is covered in BESA TR50, supports and fixings, which can be downloaded from besa.com knowledge, or it is now available on IHS. If your company subscribes to IHS, it is available on there. Hopefully that has been a good introduction to the whole subject for you. And any questions, I'm more than happy to take them.
Thanks, Will. That was a real whirlwind tour of TR50. Certainly a lot of information to take on board in one go. I think the good news is for everybody, we will provide these slides with Will's permission, and we'll publish them on our website, so you should be able to get some more information. So if you could post any questions you've got in the chat, we already have a few, which is quite good. So people are awake, Will, which is quite encouraging, so well done for that. So the first question is, are the testing loads used are static or dynamic load?
Are the testing loads used static or dynamic? I think when you're carrying out testing on site, it would only be the static loads that you would be testing. It wouldn't be dynamic loads. Do apologise, the phone's ringing again. Yes, it would be static loads, not dynamic. I'm assuming they mean pipe forces from expansion and thermal movement and stuff like that, so that's not something that would be tested.
Yeah, okay. Thanks for that, Marios. Phil Pearson's question is, how is the industry adapting to the new UCAS replacing CE marking?
How is the industry adapting to CE marking replacing? That's a really tricky one to answer, because in my view, I think that there's a lot more work to do. I know the CA marking is coming out, and I think I think the process has been extended by a year. So I think for the next year or so, if you've got CE marking, it will be accepted as effectively as a CA mark. There is some issues about where testing needs to take place, and ultimately, if it's a CA mark product, it needs to be tested in the UK. There's quite a lot more to work out in that whole arena. So unfortunately, I don't have a definitive answer for you on that at the moment.
Okay, thank you for that. One from me. I was quite surprised when you said pull testing is not the way forward. Can you just give me a little bit more information on that, please?
Well, it's the terminology rather than what we mean by that is if you go to a range of contractors or anybody for that matter in this industry and you ask them to define what a pull test is, you'll get 10 different answers. So I don't think anybody really understands what it is that they're saying. A pull test, a pull out test. Are you testing to destruction? Are you testing the load that you want to apply to it? What is it that you're trying to establish? So if you read 8539, it alludes to the fact that really it's a term that shouldn't be used. So it's a proof test which is essentially to prove the quality of the workmanship, and you'll be working out the load that you're applying, or a preliminary test, which would be a test to destruction to determine the allowable resistance for that particular application. So it's really a terminology thing. Okay,
thanks for that. One final question's come in. You discussed fixings being suitable for fire resistance. What are your thoughts on fixings being suitable for seismic events in higher risk industrial environments?
Good question. There are products that have been tested for that, and I think it would be something you need to work with fixings manufacturers on a project by project basis on. Again, it comes back to the subject I mentioned earlier on here about the fact that there isn't a UK test standard that talks about a support system as a single entity. So you might have seismic requirements for particular fixings into concrete that have been tested, and there will be ETA approvals for that, but there won't be anything in my view that covers the entire system. So the drop rods, the bearers, the fixings, and whatever that is into a metal deck or into a concrete, there won't be anything for all of that. So to some extent, it's all about proving an engineered solution and best endeavours until such a point that there is more industry guidance or standards on that.
Okay, brilliant. Well, the questions are coming in thick and fast. So your old friendly Tavis, With residual wind loads typically being hard to assess on projects, is there any outline guidance or of anchoring or sheltering of our plant and services to help overcome wind load issues?
Just read that out again. My phone started making a beeping noise and I misheard.
Right, with residual wind loads typically being hard to assess in our projects, is there any outline guidance of anchoring or sheltering of our plant and services to help overcome wind load issues?
No, in short, there isn't. I think that's something that would need to be worked on with the structural engineer. I think for me, this is where it's all about collaboration, and everybody historically puts everything into the MEP designers and the MEP arena. Oh, that's your problem. It's your problem. For me, this is as much a structural engineer's issue as possible. They will know the wind and snow, particularly the wind loadings. They should be advising, the MEP guys of what that information is, and they should be helping us to come up with project-specific solutions. But no, at the minute, Lee, there isn't any sort of outline guidance. But it's another thing to take on board and something that we can look at. Should say to Lee, by the way, he knows all about this subject because he was involved in it early days.
Well, that's why I mentioned his name, to be honest. Well, I thought I'd shame him. One from Darren Cooper. Would the fixing manufacturer be the solution to undertake the testing of the fixings? Do they offer this solution?
Good question. So they do. You need to be a CFA certified tester to carry out testing, proof testing or preliminary testing. So probably yes, but that doesn't mean that they should only be able that, because it is possible for anybody to go through the CFA certified supervisor training course. You just need to have completed that course and then have a test rig. So the likes of Hydrojaws manufacture those. But I think the first port of call would be the likes of the Hiltis, the Fishers of this world, and they would be able to assist with that. Having said that, there's no reason why some forward-thinking contractors can't take that on board themselves and start having more fixing testings carried out in-house.
Okay, brilliant. And finally, how are catastrophic loads handled, i.e. a fixing failing, overloading other fixings? So I think that's similar to the the ductwork picture image you show right at the start.
Yeah. What's the question? How are they?
So it's how are catastrophic loads handled?
How are catastrophic loads handled? I'm not sure I fully understand the question.
I'm assuming it'll be a case of making sure that the loads are suitable for use.
Well, I think the fundamental point is, and this doesn't just come to support and fixings. This is for me an industry challenge. We need to be designing everything and be able to demonstrate that everything is correctly designed. Comes back to that point earlier on, that if a client says to you, can you prove that the support and fixing system is designed and able to take the load, and you can evidence that? So really we should be moving away from this follow-on trades, the sprinkler contractor coming to site and adding on his pipe work underneath the bracketry and that hasn't been thought about. So easier said than done, but it's all about designing stuff and thinking about it and making sure that it's properly evidenced to start with. And I know that a lot of the contractors sort of the main the NG Baileys of this world and others are already sort of all over this, and it's something that the industry needs to fully get its head around.
Okay, brilliant. I think that seems to be the end of the questions. Very interesting. The fact that we've had quite a few questions proves it's a very interesting and relevant subject at the moment. So thank you very much for that. Yes, as we mentioned earlier, I think it's great that BESA and Cibse are now collaborating more and more and have become, part of a partnership arrangement, which is superb. So yeah, thank you very much on behalf of the West Midlands Committee and the attendees of this CPD. Thank you, Will, for your time.
Thanks very much for having me. I hope it wasn't too rushed.
Brilliant. Thank you very much. Cheers, Will.
Cheers.
Take care, everybody.